Hi, thanks for having me here to share about libyt, a tool for parallel in situ analysis with YT. And I am Shin-Rong Tsai, and this work is done together with Xu Xue and Matthew Turk. And a little bit about myself. I got my master's and bachelor degrees in physics at National Taiwan University, and I work on computational astrophysics and a tool for data analysis. And currently, I'm a visiting research scientist at University of Illinois at Urbana-Champaign. Okay, so this today's outline. I'll first go through our motivation. Why do we develop libyt, and how do we do it, and its application and discussions. So what are we trying to solve? Yeah, because simulation often use efficient programming language like C++ and Fortran, but many data analysis tools are written in Python. So simulation either need to write their own tools or they need to output those data files so that it can be processed and loaded in Python again later. And this is post-processing, which follows the blue line, where simulation has to first dump snapshot on hard disk and then load back into Python when they are doing analysis. So can we make Python to access and analyze the ongoing simulation data, like this orange dashed line? And this also, so that we can analyze the simulation with a much higher frequency. Yeah. So we developed libyt. libyt is an in situ analysis tool. In situ analysis tool, which is to analyze data on site without the intermediate step of writing data on disk first. So that we can explore these ongoing simulation data using the robust Python ecosystem directly. And also this provides a viable solution to analyze large-scale simulation because we no longer constrained to having them to store on hard disk. And this also lowered the barrier of using well-developed Python tools. Okay. libyt is a C++ library which builds on top of Python CAPI and NumPy CAPI. So, which means you didn't come to the wrong room because we are talking about C++ library. Yeah. And libyt can use YT and other Python packages during the simulation runtime. And this talk, we focus on how to use YT as the core analysis tool. Okay, so YT is an open source Python package for analyzing and visualizing volumetric data. And it is mostly used in astrophysics, and it also used in other domains like nuclear engineering, etc. And it has functionalities like selecting data objects, do visualizations like projection plot, slice plot. Okay, so this diagram is an overview of libyt and the relationship between simulation, libyt, and Python. So libyt is the middle layer that handles data input and output. And it also handles the data I/O between processes and between simulation and Python. So each process will have one piece of simulation code and one Python code. So when launched in N processes, N Python instance will work together to do in situ analysis in the process space of NumPy. And when simulation has done its computation job, the whole simulation paused, and they use libyt API to load data, and also use libyt API to run in situ analysis using YT and other Python packages. And once the in situ analysis is done, it goes back to the simulation computational jobs. Okay, so since YT supports parallelism feature, and libyt directly borrows it. So what libyt tries to do is to connect simulation to YT and Python using CAPI. So how does it do it? Yeah. So let's first specify on adaptive mesh refinement. This kind of data structure sometimes has its parent ID and grid edge, something like this. And to make the YT can directly borrow YT's functionality, we have to create the array for adaptive mesh refinement grid data structure that matches the one defined inside YT, so that the YT can direct borrow YT's algorithm. Okay, so when simulation will load its local hierarchy to the libyt API, and the libyt API will combine local hierarchy to for hierarchy, which contains information like parent ID, grid edge, and it creates an array using pyarray simple new. And so that this array can be read in Python, and also it can be read in C side using pyarray get pointer. So this array has a faster lookup simulation info while we are doing in situ analysis. Okay, so the array can be accessed both in C++ and Python side. Okay, so when loading the actual grid data, simulation load the pointer into the libyt API, and what the libyt does is it wraps the data pointer, which tells Python how to interpret this block of memory, like shape and its type. And it does not make a copy. And it uses NumPy array it sets NumPy array writable to false, so that Python don't accidentally change it. And this is a read-only array. So now Python can have access to actual simulation data. Okay, so the libyt also supports back communication of simulation information, which is this process is triggered by Python by calling the C extension method defined inside the libyt Python model. If Python needs something from simulation, it requests what data it needs, and the libyt C extension method will create a new data buffer, and it calls the user-defined C function to generate data inside that buffer. And once it's done, it returns back to Python. And this array is wrapped inside pyarray simple new from data. And it marked this array as pyarray owned data, which means it is owned by Python, so that it gets freed when it is not needed by Python at all. So the data is generated when Python is actually needed inside the in situ analysis. So finally, we have this libyt Python model. So we use Python object to make existing simulation data accessible by Python. And we use Python C extension method to ask simulation to do something. For example, generating data and redistribution data. And this enables back communication. And the libyt Python model only creates at simulation runtime. And each process has its own libyt Python model that has direct access to data on the current process. Yeah, so libyt is more like a window that simulation can talk to Python and Python can talk to simulation. Okay, so when Python is doing in situ analysis, the workload may be decomposed and rebalanced according to the algorithm inside that Python package. And that it is not necessarily need to be aligned with how simulation distributes the data across different NPI process. Well, it would be great if it satisfies the data locality when it is distributing job. And data locality is when a computing job decomposed according to what data each process has. For example, for NPI process 1, the Python on NPI process 1, the data it needs is 1, 1, and the process 1 has 1, 1 also. But this is not the case for other processes. And for an even more general case, for arbitrary Python package, we cannot always guarantee that they satisfy data locality. And there is also no way for libyt to know what kind of communication pattern it needs in advance. And this is also hard to schedule a point-to-point communication that fits any algorithm and any number of NPI. So libyt uses one-sided communication in NPI. This is also known as remote memory access, so that we no longer need to determine the sender and the receiver. So libyt collects the requested data on each process and asks each process to prepare the data that is requested by other rings at the shared memory. And then libyt creates an epoch. Then every NPI process must enter this epoch. And this is a collective operation. And inside this epoch, each NPI process can fetch the data without explicitly waiting for the remote process to respond. And we built a C extension method for this data redistribution process. Okay. So YT has support parallelism feature using NPI for PY. And basically, libyt supports all of them, but there are some restrictions because of that collective operation in data redistribution. For example, for volume rendering, number of NPI process must be even, because if it is odd number of NPI process, then some rings will not enter that data I/O stage. Okay, so get to some Python code. So the right-hand side is how people normally would use YT for post-processing. It loads import YT and enable parallelism feature, and then it loads data from hard disk with highlights in light green. And then this script did a projection plot and then saved the output result on root ring. And converting the post-processing script to inline is a two-line change. We just have to import the libyt front end for YT and then change how it loads data. Because basically, inline analysis and post-processing here are the same, except that in situ analysis loads data from memory and post-processing loads data from hard disk. Okay, so how do libyt actually run the Python code? Okay, so we use the previous script as an example. That contains a YT inline function. So at initialization stage, libyt use py_run simple string to import the script. And so now the Python contains that script namespace, and that namespace has YT inline function. And when we're doing in situ analysis, libyt API will execute that YT inline function inside that script's namespace. And every Python instance does the same thing. They execute the same piece of code. And the code are executed inside script's namespace so that they bring to next round. Okay, so libyt also supports interactive Python prompt. Okay, it follows the read, evaluate, print loop model and has control to every NPI process. So it gets the user input and tests it with py compile string. If it's success, it broadcasts, and every other NPI process will evaluate the code using py evaluate code to run the Python script. But if it failed, it will check if it is caused by user not done yet, like for example, the if statement has multiple lines. Then if it is true, then it will wait for other user input. If it is false, it will erase the buffer and start it all again. Okay, so we actually implement libyt inside Gamer and Enzo. The Enzo, the PR is current under review, so we only show the production run in Gamer using libyt. Okay, so the first application is fuzzy dark matter vortices, because vortices can form in density voids caused by fully destructive interference. So we use Gamer to simulate fuzzy dark matter and observe the density neural lines and their evolution at the center of the halo. So this simulation has the domain of 0.25 megaparsec, and our target region, which is at the center of the halo, is 3 times 10 to the minus 3 megaparsec, with max resolution of roughly 6 parsec. So the ratio of domain to the target is 100 to 1. So for us to fully capture this evolution, we need the snapshot for each time step is 116 gigabyte, and it needs 321 time step. So if it is done in post-processing, which is to dump every time step and then use YT to extract the uniform grid, it needs 37 terabyte. But if we use the YT, so we can call YT every time step and only dump our target region. The total disk space needed is 2.5 terabyte. So this is 15 times smaller compared to the post-processing. Okay. So this is the video after we extract the uniform grid data, and then we further process it to get the normalized density neural line. And then we use ParaView to do volume rendering to generate this video. The color map is the logarithm of reciprocal of normalized density neural lines, which highlights the fluctuation. And if we zoom into one of that for fluorescent green line, you can see which is on the right-hand side of this on the figure, and you can see clearly see the interference pattern. So with the YT, we can capture the dynamics of the vortices and also preserve the high resolution at the same time. Okay, so the next application is core collapse supernova. We use Gamer to simulate core collapse supernova, and we use libyt to monitor the gas entropy distribution by calling a slice plot at every time step. Okay, so you can see the neutron star at the middle, and also the advection region and its evolution. Yeah. And since entropy is not part of the variable inside simulation's iterative process, the entropy data is only generated when that block of grid is intersect with this slice plot. And it is generated through the user-defined C function, which in turn calls the nuclear equation of state in Gamer. So this minimizes the memory usage because libyt only generates data that is really needed in Python. Okay, so this is the strong scaling of libyt. And we use phase plot with a total of roughly 10 to the 9th data cells as a test problem. And the orange line is the result from libyt, and the blue dashed line is the result from post-processing. And the black dot line is ideal scaling. And you can see that using libyt does not add additional time penalty, and it is faster because it loads the data it's already at the memory. And for in post-processing, the data is on the hard disk, so it takes time to load back to memory. Okay, so libyt and post-processing have the similar deviation from ideal scaling. This is because libyt direct borrows the algorithm in YT. Yeah. And though the scaling looks bad when the number of processors gets large, and YT has tried to improve to eliminate the scaling bottleneck. But also that bottleneck, because there is some fixed cost, there is some overhead at large number of processors. Because how we import Python and the current data structure cannot be parallelized. So some jobs, the parallelized job to set up, catch up with the time it speeds up. So it has a bottleneck. Okay, so libyt currently only supports adaptive mass refinement grid structure and rectilinear finite volume, which is fixed resolution data. And we hope to engage more data structure, like particles, and more simulations in the future. Okay, so libyt makes analyzing large-scale simulation feasible. Yeah. And libyt can call other Python packages and has the ability to enable back communication of simulation information. So you can think of a scenario of using YT to select data and use it as an input to other Python models. Okay. So libyt reduces the gap between Python tools and simulation and provides us another way to interact with our data. Yeah. Okay, thank you.
All right, we have some time for questions. I'll ask one while people are waiting. So for Gamer, you're running on the GPUs.
That gamer run is run on CPU.
Oh, it was run on CPU.
Yes.
Okay. So a lot of Astro codes do everything on the GPUs now, right? We move everything there, leave it on the GPU, and just run.
Yeah, that is a future development plan of.
Okay, so right now you'd have to move it back to the CPU.
Yes.
In order to use libyt.
Yeah.
Okay.
Yeah, in the future probably will support using the GPU data.
Great. Other questions about libyt?
Yeah, thanks for the talk. So one of the things that we heard about a bit in the morning plenary was about how tools that are actually using the C APIs of CPython and NumPy have to do a huge amount of work to be able to maintain these. So it looks like you've done a very impressive amount of work to be able to achieve what libyt does. But can you talk a little bit about the maintenance side of libyt into the future and kind of how you and the team that built this see that?
Yeah, I have to say the current stage of libyt is at 0.1, and it's still a long distance to get to version 1.0. Yeah, and the current libyt code. It still needs to reorganize so that other data structures can implement inside it much easily. And also we also plan to make libyt can be accessible using Jupyter Notebook. And this also, this can be done by wrapping that interactive Python prompt directly. But but before this, we have to reorganize the libyt code so that more tools can be plugged in and used, and so that libyt can grow healthily. Yeah.
All right, thank you.
Anybody else? We have time for another question. All right. Well, let's thank Shin-Rong for a very nice talk.
Okay, thank you.